verifying linear combinations of higher-order derivatives. Hello, everyone. Let's begin by setting the stage for today's lesson. In our previous sections, we have already mastered the fundamental skills of differentiation, specifically how to calculate both the first and second-order derivatives of a function. Now, we are going to build upon that foundation. In this subsection, we will explore how these derivatives, along with the original function itself, can be combined using constants to form a linear equation. It is important to understand the purpose of this exercise. This process is a critical method used in mathematics to verify if a specific function serves as a solution to a given differential equation. As we move through the following slides, I will guide you through the conceptual framework and provide a detailed step-by-step example to ensure you can perform these verifications with precision. Understanding the concept. Now that we have reviewed how to calculate first and second-order derivatives, let's dive deeper into the concept of a linear combination of derivatives. Essentially, this is an expression where we take the original function, y, its first derivative of y with respect to x, and its second derivative of y with respect to x, multiply each of these by a constant number, and then add or subtract them together. To help you visualize this, the general form of such an identity usually looks like this: a times the second derivative of y with respect to x, plus b times the first derivative of y with respect to x, plus c times y, all equaling 0. In this general equation, the letters a, b, and c represent constant coefficients, which are simply fixed numerical values. Now, to verify an identity like this, our objective is to prove that, when we substitute the specific expressions for the function and its derivatives into the left-hand side of the equation, the entire expression simplifies to match the right-hand side, which is typically 0. Once we master this conceptual framework, we can look at how this is applied in the real world and the exact steps needed to perform the verification. Real-world application. Now, you might be wondering why we are focusing on these specific types of equations. At first glance, verifying these identities might seem like a purely algebraic exercise, essentially just manipulating symbols on a page. However, these linear combinations of derivatives are actually fundamental tools used extensively in the fields of physics and engineering. To give you a concrete example, consider the motion of a damped harmonic oscillator. You can visualize this as the way a car's suspension system absorbs a shock from a bump in the road, or how a swinging pendulum gradually slows down and comes to a stop. The movement of these systems is described by a second-order linear differential equation. In this physical context, the original function represents the position of the object, the first derivative represents its velocity, and the second derivative represents its acceleration. By combining these three components into one equation, engineers can precisely model and predict the behavior of the system. Understanding this connection helps us see that we aren't just solving a puzzle, but applying a method used to design everything from vehicle safety systems to architectural stabilizers. Now that we understand the why, let's move forward and look at the how by exploring the step-by-step verification process. Step-by-step verification process. Now that we understand the concept and its real-world applications, let's walk through the systematic process we use to verify these identities. Please follow along with these 5 steps. First, we need to find the first derivative. To do this, we differentiate the given function y with respect to x to obtain di by dx. Second, we find the second derivative. We simply take the result we just calculated in the first step and differentiate it once more to find d squared y by dx squared. Third is the substitution phase. We take our 3 components, the original function y, the first derivative di by dx, and the second derivative d squared y by dx squared, and substitute them into the given linear equation. Fourth, we focus on simplification. At this stage, we expand any brackets and group like terms together. This means we look for terms that share the same exponential or trigonometric base so they can be combined. Finally, we reach the final verification. We simplify the resulting expression to determine if it equals the required value, which in most cases will be 0. Now that we have a clear roadmap of the process, let's move to the next slide where we will apply these steps to a detailed example. Detailed example. Now that we have established the theoretical framework and the step-by-step process in the previous slides, let us apply those steps to a detailed example to see how this verification works in practice. Please look at the problem on the screen. We are given the function y equals 3e to the power of 2x plus 2e to the power of 3x. Our objective is to prove that the second derivative of y with respect to x minus 5 times the first derivative of y with respect to x plus 6 times y equals 0. Let us begin with step 1, calculating the first derivative. To do this, we apply the chain rule for exponential functions, which tells us that the derivative of e to the power of kx is k times e to the power of kx. Applying this to our function, we take the derivative of 3e to the power of 2x as 3 times 2e to the power of 2x, and the derivative of 2e to the power of 3x as 2 times 3e to the power of 3x. This simplifies to 6e to the power of 2x plus 6e to the power of 3x. Moving to step 2, we need the second derivative. We simply differentiate our first derivative result again with respect to x using the same chain rule. 6e to the power of 2x becomes 6 times 2e to the power of 2x, and 6e to the power of 3x becomes 6 times 3e to the power of 3x. This gives us a second derivative of 12e to the power of 2x plus 18e to the power of 3x. Now we proceed to step 3, which is the substitution phase. We take the linear combination we are verifying, the left-hand side, which consists of the second derivative, minus 5 times the first derivative, plus 6 times the original function. Substituting our expressions, we get the quantity 12e to the power of 2x plus 18e to the power of 3x, minus 5 times the quantity 6e to the power of 2x plus 6e to the power of 3x, plus 6 times the quantity 3e to the power of 2x plus 2e to the power of 3x. In step 4, we expand and simplify. We distribute the constants into the parentheses. This gives us 12e to the power of 2x plus 18e to the power of 3x minus 30e to the power of 2x minus 30e to the power of 3x plus 18e to the power of 2x, and finally plus 12e to the power of 3x. Finally, in step 5, we group the like terms to find the final result. We group all terms containing e to the power of 2x together and all terms containing e to the power of 3x together. This results in the quantity 12 minus 30 plus 18, multiplied by e to the power of 2x, and the quantity 18 minus 30 plus 12, multiplied by e to the power of 3x. Both of these coefficients simplify to 0. Therefore, we have 0e to the power of 2x plus 0e to the power of 3x, which equals 0. Since the left-hand side equals the right-hand side, the identity is verified. As we will discuss in the next slide, it is crucial to be very careful during these substitution and expansion steps to avoid common sign errors. Common mistakes to avoid. Now that we have walked through the detailed example, it is important to discuss some common pitfalls to ensure you don't lose marks on simple errors. First, let's address chain rule neglect. A very frequent mistake is forgetting to multiply by the coefficient of x in the exponent during differentiation. For instance, if you are differentiating e to the power of 3x, make sure you do not simply write it as e to the power of 3x. The correct derivative must be 3 times e to the power of 3x. Next, be mindful of sign errors. This typically occurs during the substitution step we performed in the previous slide. When you substitute the first derivative, dy by dx, into an equation that has a negative coefficient, such as minus 5 times dy by dx, it is easy to forget to distribute that negative sign to every single term inside the brackets. As you saw in our example, failing to distribute the minus sign correctly will prevent the terms from canceling out to 0. Finally, avoid the confusion of terms. Because this process involves juggling the original function y, its first derivative, and its second derivative simultaneously, it is possible to accidentally substitute the wrong expression into the wrong part of the equation. I strongly advise you to double-check that each expression is placed in its correct position before you begin the simplification process. If you can remain vigilant about these three areas, you will find these verifications much more straightforward. Now, let us move to the final slide to summarize the key takeaways of this lesson. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of this topic. First, remember that a linear combination of derivatives is simply an expression where the original function y, its first derivative y prime, and its second derivative y double prime are combined using constant coefficients. As we saw in our step-by-step guide and the detailed example, the verification process is strictly sequential. You must first find y prime, then use that result to find y double prime, then substitute all three expressions into the given equation, and finally simplify the terms. The ultimate goal of this process is to prove that the combined expression simplifies to a constant, which, as we've seen in most cases, is 0. Finally, referring back to the common mistakes we just discussed, I cannot stress enough that precision is key. Being meticulous when applying the chain rule and careful when distributing negative signs is critical to achieving a correct and mathematically sound proof.